Roja Mogola, Assistant Professor from the Department of ECE, VITW. It is my honor to read out your profile, sir. Before that, I would like to invite all of you, my fellow colleagues, all other department participants, and all other colleges participants, along with the coordinator of this auspicious FDP, Dr. T. Vishnupriya Madam, Department of ECE HOD, VITW, and the coordinator of this, co-coordinator of this event, Dr. T. Hemlata, my fellow candidate. So I would like to thank each and every one of you for giving me this opportunity first. So Dr. V. Bharat Srinivasulu sir is born in Madanapalle, Annamaya district, Andhra Pradesh, India. He did his PhD from NIT Warangal in 2022 and postdoc from IIT Patna in 2023. He did MTech from G. Pullareddy Engineering College, JNTU Autonomous, in the stream of VLSI and Embedded Systems in 2016. Sir did his BTech degree in ECE from Madanapalle Institute of Technology and Sciences, JNTU Autonomous in 2013, and is presently working as an assistant professor in Manipal Institute of Technology, Bengaluru, Karnataka, India. Dr. V. Bharat Srinivasulu has 8 years of teaching and research experience. Towards his profile, he has 40 SCI journals in prestigious academies and paper publications. He has also been listed in Stanford Elsevier's top 2% list of scientists in the academic year 24 to 25. His research interests include advanced VLSI devices and circuits, RF characterization, and distortion analysis of FETs at advanced technology nodes. Sir worked on various architectures like Tri-Gate FET, FinFET, NanoWire, NanoSheet, Dual Metagate, TreeFET, CompFETs, and Nanotube FETs for sub-5 nm technology nodes. He published numerous SCI journals in various publishers like IEEE, Elsevier, Springer, Wiley, Taylor and Francis, and IUP. Dr. V. Bharat Srinivasulu has qualified UGC NET, APR, SET, and GATE exams for multiple times. His papers are from microelectronics journals and RF CAD have received the highest number of citations for the year 2021. He is the reviewer for various national and international journals. Today, sir is with us to discuss and share his knowledge on the topic VLSI nanoscale devices and CMOS applications using quantum approach. I heartily welcome you, sir, and thank you for the opportunity.
Thank you so much. So thank you one and all for being part of this prestigious workshop. So now I would like to present my slides. So is it visible?
Yes, sir.
Yeah. So currently we would well into directly what is currently what technology node is running for fabricating a device or fabricating a chip. With quantum approach, we would like to full-fledged, we will move from device to circuit to layout level. So currently, whatever mobile phones, laptops, any electronic gadgets, whatever we are using, so we are very happy that the performance aspect is very good. So performance here means once you switch on your laptop, it is getting on within few seconds, few seconds to minutes. So this is nothing but performance calculation. So beyond that, if you are downloading any file, if you are uploading any file, you require more computational speed to upload or to download your PDF or to otherwise your data. So all this is depending upon your processor computational speed. So backbone of that, we have a chip which can able to grab that speed mechanism. We require highly efficient devices. Currently, we are also using quantum approach for these chips. So why quantum? Because we are integrating AI and ML databases. Also, the chip need to integrate all this AI and ML database to work efficiently for faster outputs. So you can see the image here. So at present, we are running 2 nanometer technology node. 2 nanometer technology node is nothing but the distance between source and drain is almost negligible, and it is it is less than 10 nanometer, and it is beyond uh, from 10 nanometer to 2 nanometer level. So you know what is the meaning of 1 nanometer is nothing but the billionth part of the human hair is nothing but 1 nanometer. So you can imagine, so the distance between source and drain is very negligible, and it is in the Armstrong level. Okay, so and the distance between source and drain is very less, and under the gate we have only one electron. So one electron is controlling the on and off action. So we came at that level. So what is the meaning of technology node? What happens if we reduce technology node? I will tell you with one example. So if you take your laptops, earlier our laptops, our computers are taking a lot of space, a lot of weight. So currently you can see your laptops almost are 1 kg. So in future, for example, if you achieve nanometer to Armstrong level of 10, 14, the distance between source and drain is zero point 0.1 nanometer or 1.4 nanometer. If you achieve that level, your laptop weight will be almost 500 grams, almost 100 to 500 grams. So you can see or you can imagine. So if you are using any aircraft, if you are using any vehicle without any electronic chips and without any electronic devices, it is highly impossible to manufacture any sensors, any without any devices and any socks. It is very difficult to manufacture any digital electronic equipment or product. So you can imagine chip is a base product for all your digital applications and electronic gadgets. So at this moment, we are trying to reduce the distance between source and drain. It is nothing but we are reducing the uh, technology node. If you reduce technological node according to the Moore's law, the number of transistors on the same area doubles for every 18 months. So, for example, if you are integrating some trillions of transistors on that small area, next 18 months, it need to increase trillions to um, hundreds of trillions. So it is like that. According to the Moore's law, the number of transistors keep on increasing. So what happens if you are keep on increasing the transistor on a small area? Definitely integration is complex. So when integration is complex, we will have short channel effects also. So we will see other mitigating parameters also. We will discuss in further our upcoming slides. So you can see here why we need to study all these VLSI devices. Why? Because so you need to know what is the building block of your chip or SoC. So definitely with that physics background or this quantum physics background, you can integrate uh, the device to circuit to layout to system on chip, and system on chip to tape out or a chip. So nowadays you see our Prime Minister Narendra Modi has very keen and interested towards fabrication feasibility towards India perspective. You can see the fabs, upcoming fabs in Tata fabs in Dollara, Gujarat, and all that. So we are going to fabricate almost 50,000 wafers per 1 month. So you can imagine the power of fabrication um, in future India perspective. Earlier, we are importing almost 80% of the chips from European countries and Taiwan and US countries. Right now, if we generate our own fabs with our workforce, definitely it is a major transformation in Indian perspective. So all these factors are very essential. Um, so you already know we have BTech VLSI, MTech VLSI, and PhDs also in VLSI, and also we have a quantum approach. So all these are very impactful. That's why we need to know all these basic concepts. So you can see here. So we have a FinFET. What is the meaning of FinFET? Means the channel is controlled from all the three directions. That is called FinFET. You have already seen the normal conventional MOSFET, where you have a source, where you have a drain, and you have a gate in between top of that. So what is the meaning of that? Means between source and drain there is a channel. So the channel is controlled by the gate, single gate. That is a conventional MOSFET. But we are moving from conventional MOSFET to double gate. So why? Because in conventional MOSFET we have only single channel.
Excuse me, sir.
Yes, ma'am.
The slides are not changing, sir. Uh, if
No, ma'am. I'm not changing the slide. This is the first slide itself.
Okay, sir. Thank you so much.
Yeah. So you can see here. This is a conventional. So this is conventional FinFET. So where our channel is controlled from the three directions. You already know this is conventional MOSFET, where you have source and drain, which is controlled from a single gate. So this is your okay. So this is your gate. So right now the electron can escape like this. So the electron can have random path. So which is not very good. So this
Sir,
this
slides
gate.
are not changing, sir. You're on the first slide only.
Yes, ma'am. I am right now in first slide only, ma'am.
Okay.
Yeah. So this gate is not able to control this electron which is beneath of this substrate. So because of this reason, we are going to double gate technology. So you can see here. So this is a double gate technology where your channel is controlled from the both the directions of your gate. So this is the double gate. Later we have moved to FinFET technology where your channel is controlled from the three directions. Okay, why we are moving from conventional MOSFET to double gate to FinFET? Because whenever we are moving to lower technology nodes, so the channel itself is very low and controlling the channel towards leakages is very difficult. That is the reason why. So from one gate to multiple gates, we are moving the architecture. So right now your laptops, your mobile phones, your smart gadgets, whatever you are using, we are using FinFET technology almost. Okay, so currently the advanced electronic gadgets, they are also using GAFETs where your channel is controlled from all the directions. So I will let you know in upcoming slides what is this GAFET and all that. Okay, so you can see here. So what is the trends? In 1971, Intel is using 8008 microprocessor for making your computers and all that. So currently 2017 we have 10 nanometer devices. So whatever the laptops you have bought at 2017 or 2016, the basic building block is a MOSFET or a FinFET, which is having a 10 nanometer distance between source and drain. This is at 2017. Right now we are in 2025. If you are buying any iPhone now, it is in 5 nanometer technology node. You are using 5 nanometer technology node of a building block for an IC with a base material of silicon or 2D materials. Okay, so you can see here. So what is the transformation?
Sir, excuse me, sir.
Yes, ma'am.
Sorry to interrupt you. So we could able to see only your title slide, sir. Your name, department, and all.
Okay, ma'am. So
That's
is it fine, madam, now?
now it is moving, sir. Please continue. Thank you.
Yeah. So we have seen. So you can see here. This is a FinFET diagram. So this is a FinFET what we have discussed, which we then or later we have discussed about GA also. So I will let you know in depth. So what is the FinFET, what is the nanosheet and all that. So this is a conventional MOSFET. Okay, at 90 nanometer we are using conventional MOSFET. So where we have a source and we have a drain and the gate is going to control the channel mechanism. Then we have a high K metal gate. So high K metal gate is nothing but we have a gate stack here. So we are reducing length of the gate, we are reducing the source, we are reducing drain. According to the Moore's law, we are reducing, shrinking the dimensions of everything. So we are also we need to shrink the metal gate and the high K poly gate thickness also, but reducing the thickness of the gate, electrons can penetrate from source to directly to the gate, which will reduce the gate induced drain leakage mechanism. So to overcome that, we have make an high K mechanism, high K gate mechanism, in such a way that we are going to stack SiO2 with hafnium dioxide, so which can increase the strength by reducing the dimensions. So this is a very beautiful concept. So that in 28 nanometer we are going to introduce high K metal gate mechanism. So later FinFETs came at 40 nanometer. So then multi-bit channel FETs came at 5 nanometer. So right now we are in 2 nanometer and 1 nanometer technology nodes where we are using 2D devices, two-dimensional devices. So 2D materials like molybdenum disulfate, graphene, all that replacing silicon that we will see in our future slides. Okay. So why we require quantum approach? You can see, unlike, for example, if you are designing a digital application of a lift, so we are making, for example, we are teaching digital design. How we are going to integrate with our current concept? I will let you take one example. For example, I want to make a lift for 5 floors. So generally, what I would like to take, I would like to take 3-bit system 000 001. So 111. So for example, I am going to make a lift. So 00 means ground floor, 001 means first floor. So like that, I am going to specifically give the bit, these bits for that every floor. So we have, so after that, what we will do, we want to make a F. What is an output here? So after this, we are going to make a K map. After doing that K map, we are going to build an expression. So after doing that expression, we are going to make a logic. So that expression we are going to convert into a NAND NOR logic, something like that. Then we are fabricating that logic. Finally, we are making a chip. Yeah, ma'am. Is it visible, ma'am? Everything okay?
Yes, sir, it is visible, sir.
Yeah. So finally, we are landing from a truth table to a chip. So we are doing truth table. After truth table, we are going to build a logic by K map. So in K map, we are building an expression. After that expression, we are making SOP, POS, and reducing that expression. Any redundancy is there, make it out and make it a compressed, reduced expression, and making that expression to a and or logic, building a block, basic building a logic design. Then we are transforming that logic design into a physical design called layout. Okay, so we have only zeros and ones, so but we don't have simultaneously 0 and 1. So this is quantum approach is nothing but, so whenever we are having 0 1 instead of that 0 1 at the same time, that is called quantum approach. So this quantum approach and VLSI are very nearer to so they are like twin sisters or twin brothers. So they are almost same. So whatever this quantum approach, we are going to make it is for building a logic block, making it to a chip with a quantum approach. Earlier we are following 0 and 1. 0
Yes,
means
sir.
input is 0. Yes, ma'am.
Sir, kindly keep it in slideshow mode, sir.
Ma'am, it is in slideshow mode only. Understanding quantum computing. So you are in this.
Second slide, sir. We are still in second slide, and it is in normal mode, sir, not in slideshow mode.
Okay, I think the slides are not running.
Mm.
Yeah. Is it fine, ma'am?
Yes, sir, it is fine, but please keep it in slideshow mode, sir.
Yeah, whenever I'm keeping in slideshow, it is not moving, I think so. Is it okay? Can I move like this?
Yes, sir.
Yeah. So you can see here, we have only 0 and 1 in normal conventional approach. 0 means logic 0 means only 0 will be there. Logic 1 means only logic 1 will be there. Output will be logic 1, output will be logic 0. In quantum computing, we have both 0 and 1 at the same time. So this is a logic. Okay, with this logic, what we can achieve? So with this logic, we can have different benefits. So quantum computing may provide breakthroughs in the simulation of quantum on nanoscale effects within semiconductor material. This is particularly relevant for modeling leakage current in FinFETs and GAA transistors, simulating subthreshold behavior at advanced technology nodes, example 3 nanometer and beyond. So if you have 0, 1 at the same time, what is the benefit means? So the accessing speed will be high and computational speed will be high. So all your processing speed increases. Because of that, everybody are running towards quantum. Okay, so you can see the what is the future outlook. Despite current limitations, integration of quantum computing into the VLSI ecosystem holds promise. Research is already exploring towards quantum enhanced optimization for chip layout. If you want to optimize the chip layout, for example, where we need to keep VDD rails, where we need to keep the VSS rails, where we need to keep the processor, when we need to keep the uh, Wi-Fi port or input and output ports. All this integration can be done manually, but if you integrate this quantum enhanced AI and ML integration, automatically it will give what is the best area. Within less area we are going to increase. This is like a floor plan automatically done by using quantum enhanced AI and ML algorithms. Quantum machine learning models for verification, quantum simulation of photonic and atomic scale components, all this can be so computed, and accuracy, all this can be increased with the quantum based approach. Okay, so because of all this we can get benefit like more speed, high computation, less power, low leakage, higher efficiency, robustness, all these benefits we will get. That is the reason why all conventional integration of chips also they are migrating into uh, quantum approach. So you can see here, so you can see my Intel slide now. Is it okay? Hello?
Yes, sir, it's okay, sir.
Yeah, I'm changing the slides. It is reflecting now, ma'am.
Yes, sir.
Yeah. So you can see here, Intel is right now they are following 3 nanometer node, 20 angstroms. 20 angstrom means it is almost less than 1 nanometer. The distance between source and drain is less than 1 nanometer. You can imagine. You can imagine the size of your laptop will be like a paper. Okay, so it is like it is mimicking your paper. So within future years, your laptops, your mobile phones, all are very sleeky, and you can roll them and you can put it in your pocket. It is very outbreaks are going to come within 5 to 10 years. All this transformation is going to happen that you can witness in future because of this AI, ML, and quantum approaches. This is making possible. So you can imagine the chat GPT, whatever you are typing, your chip is not able to process it, then you gone. So your chip should be very fast to access all the database within the server. For that, we require higher chips, high performance chips. High performance chips can be possible only with lower technology nodes. For example, the distance between your home and college is 100 kilometer. It will take 3 hours. If your distance between your home and college is 1 kilometer, you can move 100 times per day. So you can understand the distance between source and drain is 1 nanometer. Electron can move very fast with less voltage, less, so with more, without any random path, it will go in a ballistic transport. Because of all these mechanisms, the performance can be increased. Performance can be increased. For example, if you are typing something in chat GPT, you require very fast answer, but it is delaying. Why? Because your processor is not capable to integrate AI and ML models and try to get back to you. Because of all this, you are lagging and you are frustrated. Okay, if your processor speed is very high, you will get answers within seconds, microseconds, milliseconds. You will be happy, you will get whatever you want within less span of seconds. You can understand what is the meaning of technology node, what benefits you will get with the performance. Okay, so you can see here, so what IBM is following, we have seen what Intel is following, we have seen what IBM is following, we are going to see now. Like that, there are so many other VLSI companies like Samsung, Intel, Micron, Bosch Chip, NXP. There are hundreds of companies, top-notch MNCs are there. All these companies are right now in India only in design perspective, but so in future we will have our own fabs. So we will have our own design. We are going to fabricate our own chips. We are going to have our own products. Okay, so you can see the IBM approach. So IBM from 180 nanometer to 5 nanometer, how it is transforming its shape. Okay, you can see. So like FinFETs, scaled FinFETs, so new devices and new architectures, all they are in R&D mode. So okay, you can see IMEC. So IMEC, one of the prestigious institution, which is a research institution in Belgium. So they are also reducing the VDD. So you are reducing the distance between source and drain. So whenever you are reducing the distance between source and drain, you require very normal voltages to move an electron from source to drain. Your threshold voltage will be reduced. Whenever your voltage is reduced, the leakage voltage is also reduced. Whenever your voltage is reduced, your power dissipation will be reduced. Whenever you require less voltage, the battery can be run for 2 days, 3 days. So you can see, imagine the technology node transformation. If your device is made with 1 nanometer, you can use the battery for 10 days. Can you imagine? You see, if I am charging my battery of my mobile phone after 10 days, I will be very happy. Is it right or not? All this transformation can happen only with the Moore's law. So whenever you are shrinking the devices, whenever you are mitigating the leakages, and whenever you are increasing the performance, this beautiful transformation can happen. Okay, so you can see here. So we are at 45 nanometer and it is marching towards 5 nanometer. What are the different approaches we need to follow in order to increase the performance and reduce the leakage? Okay, you can see here, whenever the distance between source and drain is 1 nanometer, the leakage also increases. Whenever the distance between your home and the college is very less, if you get 5 minutes interval, you will go to your home. Yeah, so it is also like that. Whenever the distance between source and drain is very, very less, electron can try to escape very easily. This is called leakage. Whenever the device is in off state, whenever your mobile you are not using, whenever you are shut down your laptop and keeping, even though there is a small change in, like a small any heat or anything, something like that, any external parameters affects also, the electron can easily channel from source to drain. That is a major disadvantage. How can we overcome that? So that can be overcome by strain engineering, gate stack engineering, and fully depleted channel for improved electrostatics, then band gap engineering and novel materials like 2D materials. All these novel approaches can integrate. If you integrate and if you run a new novel device at a lower technology node, then you can see a beautiful transformation. Like you can run your battery for 10 days with sleeky mobiles, sleeky laptops, like a paper. It's like a paper. Your mobiles and laptops will be very sleeky, so that you can easily make them within your pockets or within your bags. Okay, comfort level can be increased with this all these transformations. Okay, yeah, you can see here. So whatever you are operating in mobile or laptop or a lift or automatic vending machine or any electronic fridge, all is logic, either 0 or 1, either 0 or 1. For example, you are talking in a mobile phone, so you want to generate a RF chip. Okay, the RF chip will be there, which can see, it will be it is like a communication. So you are making an LNA which can amplifiers and all that in the chip level. It is designed by RF design. Then analog also. So whatever I am talking, which is an analog in nature, you need to convert that analog to digital. That can be seen by A to D converters and all that. That will be coming under analog design. So like that, there is a sensor mechanism. Sensor mechanism means you already have billions of sensors in your autonomous vehicles and all that. You already know, on any aircraft there will be billions of sensors. In your homes also, you are using so many sensors, getting the light on and off automatically. You have a lot of sensor mechanisms. All that we are going to make with the chip only. Okay, then MEMS, high voltages and BCD power ICs and all that, everything is integrated by a chip. Everything is integrated. The basic building block is a device. Okay, so you can see, so we are studying one simple device. So you can see here a FinFET. So you can see here a FinFET device. So where is the source? This is a drain. This is controlled by a metal gate. So this is a buried oxide. Below buried oxide, there will be a silicon substrate, which we have not shown. So this is a buried oxide concept. So why? Because in conventional MOSFET, the electron is leaking like this. The electron is moving in a random dopant fluctuations. To arrest that, we have made a strong insulator to move electron from source to drain in a ballistic transport. Like a straight path we want, like a straight road we require, not bending roads. Here also bending roads can make an accident. Here also bending electron can give an accident. Because of that, we are insulating a strong insulator above the silicon substrate, and then we are calling that as a box concept. That is called SOI concept. You have understood this concept. So this is very important concept, SOI concepts. So here you can see I am making the 2D diagram of that, of a controlling FH channel from a gate with a gate stack. Gate stack is nothing but integrating SiO2 plus hafnium dioxide. Hafnium dioxide has more it has more electro permittivity. Because of that, it will get more strength, so that electrostatic integrity can be increased. Electrostatic integrity means you can make the device on and off perfectly. Okay, this is a nanowire where your channel is controlled from all the directions like this. So you can see the distance between source to drain is well controlled from all the directions, where width and height of the device is almost same. That's why it is nanowire. So if the width is more and height is less, then it is called a nano sheet. Sheet means more less height and more width. You have a parameter called width. With the change of parameter of width, we can change the performance. That is the strategy of nanosheet. So if we compare all these devices, if you can see here, in the first device, the device is achieving saturation levels very early. Saturation levels means the device is not performing. The overdrive voltage is not giving more rise in current. So this is not that much useful for high performance applications. So you can see here in nanowire, it is having more overdrive voltage, means the voltages are reaching peaks still with higher voltages also. In nanosheet also, you can see the major advantage of this. Compared to FinFET, nanowires and nanosheets are performing better. If your devices are performing better, your chips, your IO, your SOCs, your performance of your digital gadget will be high. Okay, so you can see here FinFET, nanosheet, and nanowire IDVGS characteristics. What is the meaning of IDVGS characteristics? Means it's the input transfer characteristics. Okay, so what is IDVD characteristics? Means output characteristics. So for any performance, by seeing the input characteristics and by seeing the output characteristics, we can able to judge whether this device is capable for on currents, better on currents, and better leakages or not. That's why we do generally IDVD and IDVD. Also, we do conventional because whether this device is achieving saturation at what voltage. Because of all these parameters, we will look into IDVGS and IDVD parameters. Okay. So yeah, so you can see here, what is on current means? On current means the at 0.7 voltage, at 0.7 voltage, the voltage is nothing but on current here. At zero voltage, that is nothing but off current. So even the voltage is 0.3 also on current, above threshold voltage, but we are mentioning here on current means high voltage, off current means low voltage. So by measuring on and off currents, we can achieve like this. We are reducing the gate, we are increasing the gate length here. Whenever we are increasing the gate length, what happening to on current and off current? On current, what happens? If the distance between source and drain is very less, then electron can move source to drain very easily. So on current can be improved. At the same time, off current also increases. Okay, that is what we have shown in the figure 4a. So you can see Dibble and SS also. Dibble and SS means sub-threshold swing. So below threshold voltage only, the electron is swinging from source to drain, which is nothing but getting on and off simultaneously multiple times below threshold voltage. That is nothing but SS and Dibble. Sub-threshold swing and drain-induced barrier leakage. That is the parameters which we have shown in figure 4b. So with increasing the LG from 20 nanometer to 5 nanometer, then what happens? So leakage also increases. Okay. So then we need to test our device robustness with your temperature aspect also. For example, you can see, so our devices and laptops and mobile phones are only used to, they are manufactured for only used to be in atmosphere, so room temperature levels. They are not manufactured if you are carrying your mobile in space or in a high temperature zones, they are not able to perform well. Why? Because the temperature is modeled for your device in such a way that it can withstand only in normal temperature levels, room temperature levels. So, but we need to test our device is capable. For example, in summer, we are suddenly changing, abrupt change in temperatures. That is the reason why if you are running a lab of any server lab, that is a general reason we need to install ACs. Otherwise, what happens? The systems will get hang. So why the systems will get hang? Because the device is getting more heated up because of external temperature. Because of that, electrons are moving from source to drain without any um, triggering from gate. So because of all these reasons, we generally install air conditioner ACs for your advanced servers and advanced laptops and systems. So that is the reason why we need to do temperature analysis for any device. What is its leakage at high temperature? What is its leakage at low temperature? We need to know which device is better for temperature variations and all that. Okay, so So up to this, I believe we have understood what is device, why we need to study device, what is a leakage, what is a technology node, what happens if you don't follow Moore's law, if you follow Moore's law, what are the benefits we will get, all this we have seen. So then we are going to migrating into digital design, digital logic. For digital design and digital logic, we need to study how our device is going to be transformed into a circuit called CMOS or resistive load inverter or common source amplifier or ring oscillator, any circuit. So in device level, we are studying, then we are going to have a IDVD, IDVGS and CGVGS characteristics of all the device at different voltages, different VDD, and we are migrating that lookup table into a symbol called CMOS inverter, PMOS and NMOS. For example, why we need to do all this analysis? Can anybody guess why we need to do all this analysis? So why we need to do all this analysis? Like 5 nanometer, I am going to run my device. So I am taking IDVGS, IDVD, CGVGS from 1 voltage to -1 volt of VDD. I am taking it into a lookup table and I am running a 5 nanometer based device circuit. For example, this common source amplifier is there. The distance between source and drain for this device of nanowire and nanosheet is 5 nanometer. I am running 5 nanometer nanowire based common source amplifier. Why we are doing all this? Because in cadence we are not able to get 45 nanometer, we are able to get only 45 nanometer technology node. Below that you can get, but you need to put $1 billion for that. So it is very difficult to get 5 nanometer node, 10 nanometer technology node in cadence platform in university level. So because of all that, we are generating our, my point. So then only we can run 5 nanometer CMOS inverter, 10 nanometer CMOS inverter, or 5 nanometer common source amplifier. Then only it can be able to generate the circuit performance at advanced nodes. Okay, so this is, you can see here, this is a single stage common source amplifier. So at 16 nanometer LG, so we are comparing the nanosheet with the width of 10 nanometer and width of 15 nanometer. If you increase the width, what happens? More electrons can transform from source to drain, which can increase the gain, which has been reflected here. The gain is 2.4 here, the gain is 6.4 here. So if you increase the width of a device, so more electrons can pumped from source to drain, which can increase the performance. So this can be seen, this can be very easily detected. So no need to do any master's or PhD for this. So if you increase the width of the device, definitely electrons can move from source to drain, so that more number of electrons, more current we will get, more current we will get, more GM transconductance we will get, more GM we will get, more gain we will get. Okay, so that is how we need to analyze a circuit or a device in university level or PhD level or research level, any level. So which, okay, then we are doing a butterfly diagram. So butterfly diagram means for any digital logic, it will have its limits. What is a 0? What is 1? 0 means 0 to 2.5 volts. It is given as 0 logic level of 0. 3 volts to 5 volts, it is leveled as logic 1. If the device has a voltage of beyond 2.5, which is not falling in logic 0 and logic 1, then it is an undetermined state. So for that, we require more noise margin levels to avoid that situation. So if a device has more noise margin levels, then it is better to work as a digital circuit. Okay, that is why we have shown here a butterfly diagram, which is having noise margin levels of high and low. We have shown here for so nanosheet width of 10 nanometer and 15 nanometer. So if we are increasing the width, definitely we are getting more noise margin levels, which we have shown, which we have shown in figure 12. Okay, so then we have came to ring oscillators. So why we need to study ring oscillator? Can anybody tell why we need to present a ring oscillator analysis in a BTech level or any analog circuit design or any digital circuit design? Why we need to show or analyze a ring oscillator? So why we need to show? Can anybody guess and tell me? So why we need to perform ring oscillator circuit for our BTech students or MTech graduates? So generally we have billions of transistors. So one transistor is interconnected to another transistor. Every transistor has its own propagation delay. So if you have billion transistors, there will be billion obstacles where you will get billions of where you will get more propagation delay. If you have 5 transistors, the delay is 5 picoseconds. If you have 10 transistors, you will have 10 picoseconds. If you have 100 transistors, you may have 100 picoseconds. So if you increase more number of transistors from input to output also, you will get more delay. Why? Because every CMOS inverter has its own propagation delay, which will be in line with other CMOS inverters. It is like a chain where the delay is from initial to final. Finally, the chip is performing very more delay. So whenever you are operating your laptop, you are turning on your laptop, it is taking 10 minutes, 20 minutes to get into your laptop. Is it fine for you? No. So we require fast accessing, we require fast processing speeds, we require fast, more performance chips. For all this, we need to study a device, we need to study the circuit performance, we need to understand what is the operating voltages, what is the frequency levels. All this analysis is done for performance aspects only, not for simply studying for our BTech level or presenting a paper. We are not doing all this analysis. There is a major analysis why we are doing that. If you know that and if you do, it is very better. That is called practical applications. We need to know why we are doing that. Okay. So I think up to that, you got some basic idea. So we are so can you able to see this slide? Up to that, you are having any doubt?
Yes, sir. It's
Yeah.
clear, sir. Yes.
Yeah, you can see here. So there are a lot of graphs in this. What are these graphs indicate? So all these are performance graphs. So you are using a basic device. If device is perfect, you can run a CMOS inverter. Circuit will be perfect. If CMOS inverter is very good, then you are going to make it into a layout. Okay, layout. It is layout means if you are doing 5 nanometer, it will take less area. If you are running at taking at 1 nanometer, it will take less area than 5 nanometer. Okay, then you are making a chip. So the chip of 5 nanometer is more area, or the chip of 1 nanometer is less area compared to 5 nanometer. Okay, if you are using 5 nanometer chip for your computer, it will take just 20 seconds to make your laptop on and getting into operation. If you are using 1 nanometer chip, 1 nanometer technology node, it will take 10 seconds. So it is like that. So performance is there everywhere. We need to check the performance in a device level, circuit level, layout level. So physical design, floor plan, layout, pre-layout simulations, post-layout simulations, static timing analysis, all this we do for that purpose only. Okay. So we are not doing anything for our sake. We are doing everything for optimizing the chip performance, power, area, PPA analysis. Okay, our major parameters are PPA: performance, power, area. If you reduce power, if you increase the performance, if you reduce area, then your product will be an outbreak. Okay, so you can see here. So you are benchmarking a device. So you are benchmarking a device with FinFET, nanowire, and nanosheet, both PMOS and NMOS. So why we have made this analysis means your CMOS inverter is a both containing both integration of PMOS and NMOS. So almost they behave opposite way. So you can see here IDVD of CMOS, both PMOS and NMOS. So it will work for NMOS will work for positive gate voltages and PMOS will get on for negative gate voltages. That is what we need to we can understand from these graphs. So you can also see here FinFET is getting saturation level at early voltages both in PMOS and NMOS, but in the case of nanowire and nanosheet, the overdrive voltage is very high because of the channel is wrapped from all the directions. Because of electrostatic integrity, nanowires and nanosheets are very capable for scaling, and they are outbreaks. So they are going to outbreak all the AML and integration of chips in server and all that. Because of that, they are using nanowires and GAFETs all over the world right now. Okay, you can see. So small current mirrors, then operational transconductant amplifiers, how it will behave in the circuit aspects, like in terms of FinFET, nanowire, and nanosheet. Gain is high for nanosheet compared to FinFET and nanowire. So you can see that analysis here. Then we have simple CMOS inverter voltage transfer curve, VTC curve, exactly how it is, whether it is ideal or not with the nanosheet compared to FinFET, nanowire, and nanosheet, which is giving the ideal behavior of ideal VTC curve that we have shown in this graph. All this graph we are teaching every day to students. We are also learning for our research. So we need to know why we are doing these graphs. So you can see here switching current of your device. Switching current means whenever both PMOS and NMOS is getting on at the same time, there will be a current. So there is a current called from VDD to ground. Whenever your PMOS is on, NMOS should be off. Whenever your NMOS is on, PMOS should be off. But at one state, there will be a there is a transition state. So at the transition state, there is a small time where your both PMOS and NMOS is getting on at the same time. At that moment, VDD is going to be getting the straight path and moving to the ground. That is called leakage. So that is the current which we are showing here. So this is a current where it is getting leaked when both PMOS and NMOS are on at the same time. So this is called switching current. Okay, like this we need to analyze. So what is the use of that switching current? What is the use of that ISC? So this ISC is very high for FinFET. So it's a nanosheet FET compared to FinFET and nanowire. So then we have seen on current, more on current, more the performance, more performance is there for nanowire and nanosheet compared to FinFET. Leakage also we have shown here. Then we have benchmark with IRDS roadmap. So we are analyzing a device. It is getting some on current. We are getting IV curves. We are getting CV curves. We are getting IDVD, IDVGS and all that. We need to benchmark whether this performance is in with respect to industry, so industry metrics or not. So for that, we are going to compare the device performance with the ITRF and IRDS roadmaps. Okay, they have already tested and they have implemented and they have benchmarked it, and we need to follow that IRDS metrics in such a way that our device is performing better. This is a useful research. Like that, we need to assure ourselves. Okay, so you can see here Dibble, GM, so transconductance. So why we study transconductance means, so how much voltage, how much increment of voltage giving increment of current. So if you are changing small voltage, if you are getting a lot of current increment, then it is more better device. So small change in voltage is reflecting high current, then it's called better. That is the parameter which we are analyzing through transconductance. So transconductance means change in voltage by, so change in voltage to change in current ratio. Okay. So then we are going to mitigate with transconductance generation voltage. So then output conductance, then intrinsic gain, GM by GD. Then we are also analyzing capacitances. You already know that our MOSFET is a planar structure, but whenever we are going to FinFET nanowires and nanosheets, they are 3D devices which has they are not planar structures. Whenever there are non-planar structures, capacitances also plays a major impact. Whenever the distance between source and drain is very, very, very less, C is equals to epsilon naught A by D. Whenever you are decreasing the distance between source and drain, capacitances are going to increase. These capacitances are going to reduce the performance. So that is the reason why you need to consider the gate capacitance, source capacitance, and drain capacitances, and you need to mitigate, you need to reduce these capacitances called parasitic capacitances to increase the performance. So you know right now what are the different parameters we are going to analyze for device and circuit and layout. Okay. Yeah. So then we came to another concept called junctionless mode and inversion mode. So if I have a conventional transistor, so I'm going to dope NPN. NPN means doping with N, then doping with P, then doping with N. Imagine the distance between source and drain is 1 nanometer. If I want to dope in between 1 nanometer, I need to dope NPN. Is it easy? It is very difficult. So because of that reason, we came to another concept called junctionless mechanism. Junctionless mechanism means there are no junctions. To make an abrupt device at 1 nanometer, it is very difficult. That is the reason why source, channel, and drain are made with the same doping. That is called junctionless doping. Inversion mode means NPN transistor. Junctionless doping means P plus P and P transistor. So why we are going to junctionless, I already told you. Whenever you are moving to the advanced nodes, precise doping is very difficult. That's why we are going with the junctionless mode compared to inversion mode. So we have compared the performance in a device aspects here. So you can see how performance is shown with the CMOS inverter propagation delay. So at 0.4 to 1 volts, so the propagation delay has been it has been impacted with some change of order of 0.1 picoseconds, something like that. You can see there. So inversion device is giving better propagation delays compared to junctionless modes. Okay, for CMOS inverters and switching current also, you can see the performance of both junctionless and inversion voltage. Then power dissipations, you can see like that. Then we have seen two analog circuits called current mirrors. So which is better device for analog devices or analog circuits, which we have shown with the current mirror example. Like that, you can present any devices, LNAs or any PLL, VCO. We can design any circuit based with the device concept, and you can take to circuit to layout to tape out. All these levels can be possible. Okay, so then you can measure the performance of your chip at the final stage. Okay, if your performance of the chip is very good, then every stage is good. Device stage is good, circuit stage is good, layout optimization is good, area is good, performance is good, power is good, everything is good. Your chip will be good. Then you can sell that chip for billions of dollars. AMD, ARM are ready to take your chips. Okay, if you are able to generate less power, less area, more performance, Intel, Samsung, they will give you trillions of dollars for your chip and they will buy. Okay, so you can see here. So you can see I already told you parasitic capacitances play a major impact in performance. So that is the reason why we are seeing an asymmetric spacer. So we are applying voltage to drain. The gate to drain distance is increased. Then it is called as an asymmetric spacer. Symmetric spacer means the distance between source to gate to drain are equal. So why I am increasing the distance between gate and drain? Because so CGD is more dangerous. CGD is more dangerous than CGS. So it is a Miller effect. More CGD, it can, as it's like a feedback capacitance. So CGD should be decreased. So if you increase the distance between gate to drain compared to gate to source, then it is called asymmetric spacer. With this asymmetric spacer concept, we are going to increase the performance. We are going to increase the gain that we have shown here. Okay, so then we came to resistive load inverters. So can anybody please can you give your version why we are going for resistive load inverters? So why we are teaching for your graduates? We are always teaching CMOS inverter. This is CMOS inverter. This is PMOS, NMOS, voltage transfer characteristics, and butterfly diagram. We are teaching. So why we are moving to resistive load inverter? So we are replacing PMOS with a resistor, and we are analyzing the performance. Okay, so we have PMOS. You already know that PMOS will occupy more space, more area on a chip. And we are widening the channel, widening the width of a PMOS transistor to integrate in such a way that electrons are majority carriers in NMOS and the majority carriers are holes in PMOS. The mobility of electrons is higher compared to mobility of holes. So whenever we are having both PMOS and NMOS and making a CMOS inverter, so if both the devices are having more equal W by L ratio, then it will fail. So why? Because electrons are majority carriers in NMOS, which are very fast. Electron mobility is very high in NMOS, which is not in PMOS. Because of that, so we are going to increase the width of the device. So whenever we are increasing the width of the device, so that the performance of both PMOS and NMOS will be equated and better symmetric curve we will get. So, but in case of resistive load inverter, so we are going to have replacing a PMOS with a resistor in such a way that so it can occupy even resistor also occupy more space on it, more area on a chip. Still, they are able to experiment like this. Then it is calling as a resistive load inverter. Here we are changing the resistance of a device and measuring how it can be impacted in the voltage transfer characteristics of a inverter analysis. Yeah. So 1 minute, I will just get to you. Yeah. So we are replacing PMOS with a resistor, and we are changing the value of that resistor and trying to get the ideal characteristics like CMOS and trying to mimic PMOS with a resistor. How beautifully this device is, or this circuit is, So by increasing the resistance value or by decreasing the resistance value, this is trying to mimic CMOS inverter. You can see in this diagram, ideal behavior is exactly VDD by 2. So if it is reaching to VDD by 2, then it is better device. Okay, with the resistance, load resistance of 50k kilo ohm, it is getting more realistic or more better voltage transfer characteristics compared to RL of some 10,000k. So something like that. So if you are changing the VDD also with the resistance value of 10 mega ohm, so you can see for asymmetric spacer and symmetric spacer. So like that we can play changing the resistance value of a resistive load inverter and trying to mimic the voltage transfer characteristics of a CMOS. So we can try what is a better resistor for your design, something like that. You can play with your resistive loads. Okay. So then it is other device called novel COMFET. COMFET is nothing but simply already nano sheets. There is a nano sheets. Nano sheets means definitely sheets are like first floor, second floor, third floor, fourth floor. If your building has 10 floors, then there will be 10 channels. So from one channel to other channel, it is like a lift. So whenever you are integrating both channel 1 and channel 2 by using a small interbridge, then it is a COMFET. Since it is like a C-shaped FET or a comb which we are using for our hair, then it is named as a COMFET. If you are making it this interbridge in middle exactly, then it is called IFET or simply called tree FET. Okay, so we are going to analyze this COMFET based memory device SRAM. So if we are doing an SRAM, then it is a COMFET based SRAM at 16 nanometer technology. 16 nanometer technology means almost the distance between source and drain is 16 nanometer, and getting 16 nanometer files in cadence is very difficult. That's why we are generating our own IDVD, we are generating our own IDVGS, we are generating our own CGVG at different voltages from 1 volt to minus 1 volt, and we are running this memory circuit. Okay, so like this, so we are having our own logic technology files or technology library files for our whatever the technology you are running at 1 nanometer, 5 nanometer, you can generate any device. Okay, so like this. So I already told you what is ion IF, SS, Dibble, performance parameters like on drain currents and all that. Simply to show you how it is impacting, I have represented this slide. Okay. Then we are moving to temperature aspects. For example, nowadays you are seeing, so suddenly there is a blast in a vehicle. Because of the change in temperatures, electrons are getting heat, electrons are migrating a lot, and they are having a lattice temperature effects are also increasing because of the collisions of that electrons can make it electric sparks, so which can blast your device or blast your vehicle or blast your laptop or blast your mobile phones. So overusing of your mobile phones or overusing of your laptops or overusing of your digital gadgets, you should be you should take more care at that aspect. So okay, otherwise what happens, you already know thermal breakdown will happen. Because of thermal breakdown, your device may sometimes it may explode also. So you need to take all these aspects. So here we have seen the lattice temperature. So you already know your laptop is having a processor which is very small. You are using i5, i7, processing speeds are very high. Whenever your processing speeds are very high, your device also, your laptop also get heated up within less time. Because of that heat, because of you are using a silicon SOI technology, that heat you are not able to dissipate in substrate. Instead of substrate, you are dissipating towards metallic contacts. Earlier we are using aluminum metallic contacts. Because of this heat, aluminum is also melting up. So nowadays they are using titanium nitride and some gold and some other materials, and all these aspects plays a major role. So then okay, so if you have more device space, you can dissipate this temperature. For example, your house is 1 BHK. If you are getting more heat, it is in that area only. If you have 2 BHK, the heat can be dissipated in 2 rooms. If you have 3 BHK, the heat can be easily flowed out, something like that. If your device is very complex in nature, dissipating heat is very difficult. Okay, if you are working at 1 nanometer processor, the laptop, 1 nanometer based laptop or mobile phone, definitely you will get, it will be pumping a lot of heat. How to reduce that heat is a major challenge. Okay, getting sleeky mobiles, getting less weight laptops or mobile phones, it is very easy. We are advancing, but how to reduce the heat is a big concern. So we are playing with different material engineering is playing here, which can compensate this heat outpass. Okay, so one of them is 2D materials. Okay, so I'm taking more time, but I will cover up within 5 to 10 minutes this 2D material concepts. So why we need to use 2D materials? So we know in our practical life we are seeing gas sensors, supercapacitors. Capacitors is nothing but your charger. Solar cells, you are using your solar batteries for your household applications and beyond that. And you are using batteries everywhere, interconnects, flexible displays, touch panels, field. So all these are having base material as a silicon, but whenever you are migrating to 1 nanometer, your silicon is not performing well. So that is the reason why we are going to replace your silicon with 2D materials like MOS2, graphene, black phosphorus, morphine, and SNS2, MOO3, something. These are different 2D, different types of 2D materials are available in the market. You are going to study the properties of that, which is very flexible for the performance, leakage, and you are going to adopt that for your channel. Okay. So one of the work which we have done is we have taken molybdenum disulfate, MOS2, and MOSC2, MOTE2, all these 2D materials, how it performs with gate dielectric, uh, changing the gate dielectric we have shown in this slide. We are changing LG and changing the dielectric, how your performance is impacted, which we have shown in this figure. So this work is done by open source platform called nanohub.org. So which is very useful platform. It is an open source. I will give website also, you can go and explore that in that. So all these parameter metrics, on current, off current. So all these parameters we have taken in the open source platform itself. Okay, so I will show you the open source platform, how it will be operated. So you just go to the nanohub.org. So can you able to see my slide?
Slide,
Nanohub.
okay, sir, but that NanoHub environment is not
Yes, ma'am. So I
showing
have
graph only.
yes, yes. Am I audible, ma'am? So can you see my screen now?
Yes, sir. It is audible and it is visible, sir.
Yeah, you go to nanohub.org, which is an open source platform. Just enter. Okay. So then explore tools. Then nanomass. Just simply type nanomass. There are n number of tools will be there. Control C, Control A, Control C. There will be a number of tools will be there. You can go to nanomass. Okay. So there will be a number of tools will be there. You can explore that. All these are 2D. You can see 2D FET. If you go to the 2D FET, go to launch tool. So it will ask your Google to link with your Gmail. Okay, then your simulator platform will come. Can you able to see here molybdenum disulfate is a 2D material. It's a CMOS type. You can type it into PMOS also. Okay, so then you get just go to simulate. You will get IDVGS characteristics. So if you want IDVD, you will get like this. If you want CGVGS, you will get like this. If you want change the material to black phosphorus, so simulate. It will take some time and you will get IDVD. So then CGVGS. So if you are changing the N type to P type, simulate. One minute, yes. So P type hole. So we need to apply voltages. Negative voltages we need to apply here. Okay. So you can play like this. In your free time, you explore these tools, and if you have any doubts, you try to message or what, so something like mail us. So we'll try to. Okay. So yeah, you got the simulation output from 0 to -5 volts. So it's a PMOS characteristics. So you can change the voltage to 0.8 to -0.8 also. Like this you can play. So are you able to get this? Are you able to see this?
Yes, sir. It is clearly visible, sir.
Yeah. Like that, there are other tools also. Open EDS tool. For example, if you are having your institute don't have any cadence platform, any circuit platform, you can use this platform. Just make it CMOS, just make it PMOS. So you just connect it, and you can run your CMOS inverter design like this. So make it ground. So make it VDC. Okay, you can make it V. So voltage. So then simply just you can run it. Okay, and you can check it something like this. Okay, so you can design any circuits. Nowadays everything is open source. You can design anything. So what is the technology node here? What is the technology node here? GPDK. You can see here. What is the technology node? Can anybody answer? What is the meaning of 045? So am I audible? Hello.
Sir, yes, sir. It is 45 nanometer technology, sir.
Yeah, so it is at 45 nanometer technology node. I have all the options here. Simulation option is there. You will get the analog design environmental window. You can simulate here. You will get all these options are available. It is your version how to work. Nowadays, everything is open source. 45 nanometer, you are using cadence by paying 30 lakhs for 3 years. Same environment is there in open source also. You can work here, you can analyze here, you can design here, and you can write a paper. Everything is free. Okay, so like that, there are other so many platforms also there. If we get any time, we will explore into that also. I think if you have any doubts, I am restricted to 1 hour 30 minutes. I think I'm almost near to that. I have 10 minutes of time here. If you have any doubts, you can post me here or you can ask me. I would like to reply or I would like to explore for that.
Requesting the participants to raise your voices if you have any queries.
So I believe, have you understand all these concepts?
Sir, can you please tell me the software, free software, open source software again, its name?
So nanohub.org, nanohub.org. So I'm just typing here. Please you can.
Okay, sir. So can we
Nano,
simulate a complex circuit also, sir?
can we simulate?
Complex circuit also.
Yeah, you can simulate a device from device to circuit. You can do in nanohub.org. You can study material properties. You can study device properties, 2D material, silicon-based device, nanowires, nanosheet. Everything you can do it in nanowire. If you want
Okay, sir.
to,
Can we have the power and delay calculations of
that only,
the
man.
circuit also, sir?
You can do it in open source circuit platform. For example, if
Okay.
you have a library of 10 nanometer, for example, you have the all device characteristics at 10 nanometer in nanohub.org, IDVD, IDVGS, and CGVGS. You can make a
Okay.
lookup table and try to migrate it into Cadence platform or in a circuit
Okay.
platform with this library files. Understood?
Oh, okay, sir.
Yeah.
So for our purpose, for our simulation, for our clarification, we can simulate and we can transfer it into Cadence, right?
Yes, absolutely.
Okay,
Yes.
sir. Okay, sir. Thank you. Thank you.
Yeah.
Thank you, sir, for your valuable session. I would like to give a quick brief regarding what are all the discussions that we have gone through. So first and foremost, how distance between source and gate, a little distance between these two impacts the speed and operation of our device, and how it increases the when the distance is being decreased, how the performance is being impacted, and how the material changes impacts the speed of the processor and device, how quantum computing comes into picture and affects the VLSI ecosystem, nanoscale devices, and the chip design. What are all the advantages of using quantum computing on VLSI design and chip design? And what you have clearly explained all these things with the statistical representation and the image representation, sir. And the performance check at different levels before and during the design and manufacturing of the device achieves performance optimization and helps to achieve performance optimization has been clearly explained with your expertise knowledge in the research and development of your PhD and postdoc work, sir. And how parasitic capacitance is decreasing the performance. What are all the novelic approaches that we have in order to decrease or to avoid all the disadvantages that we may go through when we have such issues. And thank you so much, sir, for your hands-on and lively interaction on using the open source simulation using nanohub.org. I would like to thank you so much for your interest in this FDP and for hosting us, sorry, for investing your personal time in enlightening our knowledge on quantum computing or quantum approach related VLSI nanoscale devices. Thank you so much once again.
Yes, thank you. Thank you so much. Thank you all participants for your kind and patient listening also. Yeah, thank you.
One second, sir. I request all the participants if they are willing to turn on their cameras so that we can have screenshots.
Yes, sir. Thank you, sir.
Thank you, Bharat sir, for your session and your time investing. I would request the all other participants to wait for 5 more minutes for next session. Thank you. Good evening, Maheshwara sir. Seeking for your permission to start the session by, if you allow me to read your profiles.
Yeah, you can proceed.
Thank you so much, sir. So first of all, welcome to the session, sir. It is my honor and privilege to read out your esteemed profile. Good evening, everyone, once again, and here I am to read out the profile of Dr. Maheshwara Valluri, sir. Dr. Maheshwara Valluri is a researcher, educator, and entrepreneur at the forefront of quantum computing, communication, cryptography, and emerging technologies. With over 2 decades of academic and industry experience, Sir has contributed extensively to quantum algorithms, hybrid quantum classical systems, and post quantum cryptography. He holds a PhD and currently serves as the founder, CEO, and chief scientist of Infosys Private Limited, where he leads multiple product lines and global collaborations connecting quantum engineering and technologies with real world applications. Dr. Valluri, sir, is also the director of QEDX, an advanced platform for training and certification in quantum computing, AI, cybersecurity, and emerging technologies. Prior to returning to India in June 2023, he held senior academic and research positions worldwide, including at the University of Technology and Applied Sciences Oman, Fiji National University FNU, where he has served as head of school mathematical and computing sciences, associate dean, and executive council member at the University of Auckland, New Zealand. Dr. Valluri played an active role in higher education accreditation, collaborating with RMIT University, Melbourne, Australia, on frameworks aligned with the Washington and Dublin Accords. With over 30 research publications, his scholarly work spans quantum computing, cryptology, and secured system design, emphasizing the connection between rigorous theory and practical experiences. His research and innovation have received global recognition, including the IEEE Best Paper Award in 2016 at the World Congress of Industrial Control System Security, London, for his encryption algorithm. Sir has delivered talks at prestigious institutions such as University of Cambridge, UK, and the University of New South Wales, Australia, and has undertaken academic visits to many countries. He is a professional member of leading international organizations including IACR, IMA UK, and AMS USA. As an entrepreneur, Dr. Valluri envisions quantum technologies as enablers of scalable and intelligent digital ecosystems. At Coinfosys, he leads initiatives in quantum safe security, quantum AI, quantum databases, and quantum web services. Through QEDX, he empowers learners worldwide with practical quantum programming and emerging technological skills. Currently, Dr. Valluri is spearheading the Quantum Research and Education Consortium (QREC) with Amravati Quantum Valley, collaborating with Indian institutions such as Andhra University, Sri Venkateswara University, JNTU-A, Rayalaseema University, Siddhartha University, and Gayatri Vidya Parishad College of Engineering. Through his custodian, he aims to build a robust ecosystem for quantum research, training, and innovation in India, bridging academia, industry, and government efforts. So, once again, a hearty and warm welcome to you to start our session, sir. Thank you.
Yeah, thank you for lengthy introduction. And so are you able to see the screen?
Yes,
I
sir.
may start sharing the screen. Okay, so I have been requested to deliver mostly the fundamental concept of quantum technologies. So I covered some of the mostly my focus in this talk on quantum circuits and analysis of the circuits. So perhaps in the next session that I will be giving about the quantum search algorithms and hands-on some of the hands-on for those. So let us begin our journey for quantum technologies. Actually, what is a quantum computer? That's a primary question that everyone should ask themselves. A quantum computer is also a physical device that how we have classical device, but only the difference is in the computation process we use classical bits, zeros and ones, which we represent abstract approach for the electronics behavior like electronics spin up, spin down energy. Likewise, we use for photonic or other superconducting materials of behavior. In terms of that, we represent in terms of qubits. In abstract manner, we represent that either ket 0 in classical representation for this column vector. Sorry, I put it other way. I want to correct this, so sorry. It should be 1 0 and 0 1. By mistake, it happened. I correct it and submit again. So qubits are governed by the laws of quantum mechanics. Actually, this should be other way around. It should be 1 0 and 0 1. Please take a note. Ket 0 equals to 1 0. Ket 1 equals to 0 1. I put it other way by mistake. But take a note that otherwise it confuses a lot. So qubit can get in the superposition at a time simultaneously. This is a representation. Suppose if we take a photonic light, suppose if we switch on the light, that light can provide a brightness in the entire room. That itself is the superposition state of the photon. So which enables the to represent both ket 0 and ket 1 simultaneously. They also exhibit entanglement. Entanglement is nothing but the two particles can correlated one another irrespective of the distance. This is a mysterious phenomena which we can see in quantum system. And the third one is a quantum interference. Suppose you have two two stones. You put it those two stones in water simultaneously, then what happens? Waves come and interfere one another. So this is the behavior again, which you can see in quantum interference, which are key phenomena that allow quantum computers to solve certain problems exponentially faster than the classical. What we can understand that qubit representation in quantum process for representing data, and also superposition, which is a very interesting phenomena which we can see well in quantum and entanglement and interference. The picture that we displayed here is a superconducting based quantum computer. Naturally, we need to use in this system cryogenic engine, which can bring the temperature into Kelvin temperature, 0 Kelvin temperature. 0 Kelvin temperature, which is equivalent to in terms of Celsius, minus 273.15 degrees Celsius, in which we have to maintain. To maintain that kind of temperature, very low temperature, I mean negative temperature, we need to use a cryogenic engine. In bottom of this, we can see that the quantum processor and quantum controller. Naturally, this can be around 3.5 meters, and each chamber brings down the temperature. So from room temperature to, for each chamber, we use to bring down the temperature to minus 50, minus 100, like that. Okay, someone is using something. Stop using that. Something scratches on the screen. So what is the quantum computer? What is a qubit? A qubit is the basic unit of a quantum information, which is analog to a classical bit, but with the distinct differences stemming from quantum mechanics. So naturally, we can represent the abstract manner, the qubits, uh, by using blow sphere, and in which we use Hilbert. This is a space called Hilbert space. Hilbert is a mathematician. In this space, we can represent in abstract manner. Basically, qubits are prepared using certain kind of materials, like superconducting materials, trapped ions, or, or topological qubits, or some other kind of materials. Okay, a qubit can be described as a vector, which we represented beginning. A qubit ket 0 equals to 1, 0, ket 1 equals to 0, 1. We could see that. So in two-dimensional Hilbert space, so this is a complex space which we represent. To representing one single qubit, we need to use two classical dimensions. So that's the reason we use 2 C power n. With the two possible bases, ket 0 and ket 1. Okay, so naturally, the superposition of these two, ket 0 and ket 1, we can represent using any wave function, that any quantum qubit state wave function can be written as this form. Ket, this is the Dirac notation, ket notation. Ket xi equals to some amplitude alpha times ket 0 plus beta times ket 1, where ket 0 and ket 1 are the two computational bases, and alpha and beta are amplitudes in physical representation, whereas in terms of mathematical representation, we can put it as a complex numbers. And it has to satisfy the normalization condition, ket alpha square plus ket beta square equals to 1, which ensures that total probability of measuring the qubit is 1. So I explained this scenario in another manner, that if you have a coin, you take a coin and keep on table and rotate it. When it rotates, after it rotates, sometimes after energy drops, what happened, that coin drops down and it can provide output either head or tail, right? So likewise, that we can represent as head or tail, that we can represent ket 1 or ket 0. But during spinning, we don't know the state. That state is this ket xi equals to alpha times ket 0 plus beta times ket 1. We don't know that alpha beta amplitudes, but if you keep that state in standing position, then we know that exactly the amplitudes, then we can easily measure it. So right. So this is the qubit representation. It is a bit different from classical representation, in which we use mostly linear systems rather than abstract. Right. How to prepare qubits? Because we are talking in terms of abstract manner, mathematical representation of these qubits. How do you represent these? How do you prepare these qubits using physical materials? We know that we can prepare zeros and ones using semiconductors, right? Electrons. So electrons behavior, like how do you prepare qubits? So that's the most challenge in today's world. What kind of material we can use to prepare qubits? Qubits can be implemented using various physical systems, each with the distinct advantages and challenges. We discuss few of them. One of the famous material that they use for preparation of qubits, superconducting material. Superconducting material, even IBM, Google AI, and also Rigetti, these companies have been using superconducting materials. And the scalability, which we noticed, we see that quantum computing is also available today. So in the methodology they use here, Joseph junctions in superconducting circuits, the advantage is the system fast gate speeds and scalable via chip fabrications. Second kind of material is a photonic qubits. Photonic qubits, using photonic qubits, we can encode information in photon polarizations and or path actually. The advantage of this photonic qubits, low decoherence, suitable for quantum communication, and also we don't require to use that cryogenic engine. It can work at room temperature. This is a major advantage of the usage of photonic qubits. Third one is trap dance. So mostly trap dance based quantum computer is built using by IonQ company, US-based company, trapped ion qubits they use, which uses internal electronic states of ions trapped in electromagnetic fields. So the advantage of this system is high fidelity and long coherence. Next material is quantum dots, in which they use electron charge or spin in semiconductor nanostructures. The complementary metal oxide semiconductors compatible and compact. This is the advantage of this system. Next material, neutral atom qubits. They use ultra cold atoms trapped in optical. Advantage of this system, scalable arrays with a long coherence. Another one is topological qubits. Even Microsoft recently advised that they are going to use that Majorana chip. So Majorana was identified in 1937 itself. There is non-abelian noise, which offers intrinsic error protection, but it is still under experimental stage. Next one is a spin qubits in silicon, which uses single electron or nuclear spins in silicon, which integrates with the semiconductor technology. The advantage of this system is the long coherence. Final one is a nitrogen vacancy center in diamonds, which mostly we use in a sensing technology, which operates at room temperature, uses spin states of nitrogen vacancy defects in diamonds. So these are the materials that they use. So for preparing qubits, but we see that each material has certain advantages, certain disadvantages we need to handle. And the major thing that we need to have quantum processors which can provide the data processing and also storing the data. These are the challenges. So scalability is another one. If you have physical quantum devices, we can be able to handle any kind of computation and communication and sensing. So these are the identified material as of now. Perhaps there may be new material may come in future. Right. I described about discussed about superposition. What is superposition? Quantum superposition is a fundamental principle of quantum mechanics where a quantum system can exist in combination of multiple states simultaneously. So that for a single qubit case, we can represent superposition ket xi equals to some amplitude alpha times ket 0 plus beta times ket 1, where alpha, beta are amplitudes as we discussed. The absolute value square is the probability of measuring the system in state 0, whereas absolute value beta square is the probability of measuring the system in state ket 1. And also it has to satisfy total probability is 1. Suppose if you take a coin and you keep that coin in a standing position, but don't drop down, and keep it exactly standing but not rotating. That what is the state of that? We can describe that ket xi equals to 1 by square root 2 ket 0 plus beta times ket 1 by square root 2 ket 1. So if you measure that, so 1 by square root square, which equals to 1 by 2, 1 by 2 equals to 0.5. 0.5 is a 50% chance to be having output get 0, whereas 50% chance to have uh, output get 1. So we can see that if you take a coin, 50-50 chance to be head or tail, that's we can put it that as a best example for representing that superposition of single qubit. But this allow a qubit to be in both the states, get 0 and get 1 simultaneously until measured. Upon measuring, that state collapses. We know that we can get the output either get 0 or get 1, and we can measure that. Right. So if we have 2 qubit system, but we can generalize this system into n qubits, and also we can use tensor product to multiply the uh, dimensions of the system. So the state of 2 qubit system is a superposition of all possible basis states in 2 qubit Hilbert space. For a 2 qubit Hilbert space, we need classically 2 power 2, that is a 4 dimensions, so C power 4. If we take 3 qubits, we need to have 2 power 3, 8 dimension. If we take 4 qubits, we need to have 2 power 4, 16 dimensions. So likewise, if you have 10 qubits in Hilbert space, you need to have 2 power 10. 2 power 10 equals to 1024 classical bits, which equals to 1024 dimensions. So that's the way we can represent classical versus quantum. So let us discuss for small scale to understand this. It can be expressed as get psi equals to some amplitude. So these amplitude actually equally distributed in superposition, but we are using, if we take 2 qubits, there are 4 possibilities. One is we can represent even in classical system 0, 0, 0, 1, 1, 0, 1, 1. So if we take 2 qubits, we can represent 0, 0, 0, 1, 1, 0, and 1, 1. So you can also put them to 0, 0, 1 equals to 1, 1, 0 equals to 2, 1, 1 equals to 3. We can represent that get this amplitude times get 0 plus amplitude times get 1 plus amplitude times get 2, amplitude times get 3. So this is how we can represent. These are the alpha, this alpha is the subscriptions are the amplitudes in physical system, whereas if you want to represent in terms of mathematical, that's the just complex number. If you take absolute value of this and square it, and the total must be equals to 1 because the probability always 1. This is how we can represent in terms of Blow sphere, right? I use IBM Composer. I can show you that how we can put it. So I stop using for a second, then I'll come back. I share another screen. Yeah, I am using IBM Composer. If we take 2 qubits, I'm taking 2 or 4 or any qubits. You can take, for example, I'm taking 2 qubits. I am representing these 2 qubits in terms of, are you able to see the screen? Please confirm. Anyone can
Sir, it's visible, sir.
Right.
It's
Thank you.
clear.
So this is a cat 0, cat 0. So actually we need to keep the system in ground state. Both are in ground state. We can also see output. Or if you want, you can put it in 4 qubits. You can also change into 4 qubits. I'm putting into 4 qubits. So if we are putting in 4 qubits and mission in the ground state now, this is the ground state of the mission. We represented this. I'm using for this superposition. In order to bring into superposition, we need to use Hadamard gate. We will be discussing about Hadamard gate. This is Hadamard gate. So this is for single qubit. I represented. Actually, if you want to represent single qubit, we can represent in terms of this is single qubit. So if I use the Hadamard gate for single qubit, it is in 50-50 chance now. See, 50% probability for state 0, 50% probability for state 1. So we can represent geometrically like this. So now I'm putting this 2-qubit system. If you use 2-qubit system, I use 2 qubits zeros actually. Sorry, I made a mistake in representing qubits in my slides. You should take carefully. And I correct, and when I submit, again, I submit the correct version. Sorry for that mistake from my side. Now, look at this. If we take, as I mentioned, 0, 0, 0, 1, 1, 0, 1, 1, these four distribution, probability distribution in superposition, equal distribution, 0.25, 0.25, 0.25, 0.25. This is geometrical representation series. Now I am increasing one more qubit, 3 qubits. If we take 3 qubits, then I am also taking 3 qubits now the data in terms of, if we take, there are 3 possibilities, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So total 8, right? This is equals to 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 110, then 1. Now I put them in superposition now. See, equally distributed again, 12.5, 0.125, 0.125 probability. Total probability must be equals to 0. So if we take 4 qubits, I'm taking 4 qubits, 16 dimensions actually. You can see 16 dimensional blow sphere here. This is 16 dimensional sphere. And you can see this. Now put it, this is next one is here. So this is 16 dimensions, you can see equally distributed. This is superposition. We could see 16 people at a time. This is the blow sphere for this representation, right? So this is the representation for superposition of 16 dimensions. I mean 4 qubits. Yeah. Yeah. I would like to continue. Yeah, so we can generalize this for n qubits. For n qubits, the total state of the system is represented by as a vector in combined Hilbert space. We use c power 2 power n, and the state can be written as superposition of 2 power n base states that we represent by using wave function ket xi equals to sigma x equals to 0 to 2 power n minus 1 amplitude times kx, where kx is one of the 2 power n possible basis states of the system. So we can represent the ket representation, the qubits, we can put them, increase them and multiply them using tensor product. And in terms of classical system, we need to use a dimensional multiplication, for which we use tensor products. And we need to answer that normalization condition as well. This is the normalization condition. Next one is quantum entanglement. Quantum entanglement is a phenomena where two qubits or more than that quantum systems are correlated such that the state of one qubit can't be described independently of others, irrespective of the distance. So which we can represent by Bell states EPR pairs. These are the 4 possible EPR pairs per 2 qubit system. These are the 2 particles which are interacting one another, and this is the image, just a image for representing entanglement. They are in correlated one another. It's more like in terms of human aspects. If I want to represent this two souls, once they connect, irrespective of the distance they connect, it's called love. Likewise, even particles can fall in love. So irrespective of the distance, they can interact. So this is a similar behavior. This is a mystery. And for this, recently, in 2022, Nobel Prize was given for experimental work of this quantum entanglement. Next one is quantum interference. Quantum interference arises from the superposition of the quantum states where probability amplitudes combines constructive or destructive affecting measurement outcomes. There are two, as I mentioned, that two stones, if we put in a water, we can see that the waves are coming and colliding, and interference happens. The interference can be constructive or destructive. Actually, if you look at this 2-qubit state, so if you take 2 qubits in the superposition, there are 4 amplitudes, right? But in for the same 2 qubits, if you take in entanglement, 2 amplitudes are missing out. That's distraction happens due to interference. So that's the example for explaining constructive and destructive interferences, right? So naturally, that's a fundamental part of the quantum mechanics, mostly part of the quantum physics. Let us go for the little bit circuit aspects. Quantum circuit, how we can build the quantum circuit. Actually, this is the model circuit that I represented here, that how we take the quantum circuits. Quantum circuits consist of sequence of quantum gates, which we use to perform the computation, right? So we represent each line as a qubit, and gates subsequently one another from left to right. So qubits are typically initialized in the state of ground state. That's one of the criteria. Then we apply gates here. These are the gates, and gates are used to manipulate the data. So there are numerous gates that we use: Hedemard gate, Pauli gate, G gate, control NOT gate, control G gate, swap gate, Toffel gate. There are many other gates that we use. Finally, we measure the system, which crosses quantum qubit state into computational basis, where we can measure classical bits. So the few gates like I gate we represent in terms of matrices 1 0 0 1. If you apply I gate on qubit 0, there is no change. Even apply on I gate on qubit 1, there is no change. Like how we have negation gate, NOT gate in classical system, that likewise we have NOT gate on quantum, that we represent by matrices 0 1 1 0. This circuit representation, symbolic representation for Pauli X gate. And if you use X gate on qubit 0, it flips into 1. Likewise, if you use on qubit 1, it flips into 0. Then Pauli G gate, so Pauli G gate is also called phase gate. We write Z equals to 1 0 0 1. This is symbol for representing Pauli G gate. If you apply G gate on qubit 0 0, if you apply 1, it shifts the phase minus. And likewise, we have Y gate. Y gate equals to I times X times G, equivalent to Y gate. We represent 0 minus I 0. This is the representation. If you apply Y gate on qubit 0, I times gate 1. If you apply on qubit 1, it flips into minus I times 0. So this is the T gate. T gate also it shifts phase globally. So we can use for different, we put it to T equals to 1 0 0 e power I pi. Pi can be, you can change the pi value. And if you apply on qubit 0, it does nothing. If you apply on qubit 1, e power I times pi, get 1. So Hadamard gate, we use Hadamard gate for bringing the into superposition. Again, if you apply Hadamard gate and superposition, it brings back into computational state. So it's one of the important gates. If you apply Hadamard gate and qubit 0, it brings into superposition. And if you apply Hadamard gate and qubit 1, it brings into superposition with the negative sign. That we represent ket plus, ket minus. Matrix representation for representing Hadamard gate 1 by square root 2, 1, 1, 1 minus 1. This is how we can put them. And this is the symbol for representing Hadamard gate, which you might have noticed in the system before. Likewise, control NOT gate. Control NOT gate, we represent Cx equals to, here this part identity 1 0 0 0 0 1 0 0 0 0 0 1 0 0 0 1 0. So this is the circuit to be represented 2 qubits wire, and also we are applying control NOT gate. So the first wire X, it remains same, whereas second wire is controlled by first wire. Output or target get X, X or Y. And if you apply, we can apply this on 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. If you apply on cat 0, 0, first wire and second wire, using this circuit, we can also represent 0, 0 remains 0, 0, 0, 1, 0 remains same. Only in the case here, it flips 1, 0 case 1, 1, 1, 1 case 1, 0. Likewise, control NOT gate we represent, control Z gate we represent. This is the matrix representation: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1. This is the circuit. First wire same, second wire only shifts by phase minus power of this first qubit. Suppose the first qubit 0, positive sign, first qubit 1, negative sign. So this is the what it happens. This is the output. So basically, we apply gates for manipulating the quantum information. Likewise, another gate, swap gate. Swap gate swaps the information. First wire we have qubit 1, second wire we have qubit 2. This information swaps into this, that. For gate representation for swap, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. So what it can do that first qubit flips into second, sorry, swaps into second one swaps into first. This is the action of the swap gate. Likewise, important gate we have Toffoli gate. In Toffoli gate, we apply on 3 qubits wise, and here we use the quantum resistors. Here we take 3 wires actually: first wire, second wire, third wire. First wire remains same, second wire remains same, third wire is controlled by first 2 wires. So we represent Y, XOR B and X. This is the representation. And we can see if you apply, if you take 3 qubits, we have representations 0, 0, 0, 0, 0, 1. Like that, we have 8 ways so we can put them 3 qubits. So we have 8 by 8 square matrix for representing CCX gate. This is the gate representation gate for CCX in terms of matrices. And we can see that you can apply these swaps 1, 1, 0. If you apply CCX on this into 1, 1, 1, 1. So you can see this. Next one is classical register to quantum register. You have classical data. We have keyboard. In our keyboard, we have how many keys we have? Anyone can tell? We do have on keyboard 256 keys actually in our keyboard. ASCII code we have assigned values. Then when we type anything, that will be converted into low-level language in binary code. That conversion happens. But how do you map into quantum information? We do have keyboard in terms of classical information, but we are doing the process in terms of quantum. How do you convert that into? So we need to use some kind of mapping, which is called encoding process. A classical register of n bits that we represent by C by taking each element from the size, the set get 0, 1 with the size n, which is encoded into quantum register of n qubits by representing this. So this is an example for representing classical register 1010 of 4 bits in terms of quantum. Cat 10110. Right, now we do have a technique and process that we can map classical information into quantum. We can do that. So how we can do that, the classical into quantum, by using this technique. This is the binary data. So we can use the XGate, this is the XGate, and also use tensor product operator, get k equals to 0 to n minus 1 bk. If you do this process, you will be able to convert classical data into quantum data by processing. But we can also put actually one of the criteria that we need to keep the mission in ground state. Using this criteria, we can map the information into quantum. This is the procedure for mapping the classical information into quantum information. So this is an example for this processing, converting classical bits into quantum bits. And we also need to encode the amplitudes. So for which we use vector space concept, and we take the classical data in terms of vector that we represent vector x, which is in the domain of c power 2 power n, and we take 2 norm, we compute the values and the corresponding alpha i's using this formula xi by norm 2, and the corresponding quantum state can be constructed using this mapping from x to get psi equals to sigma I equals to 0 to 2 power n minus 1, some amplitude times I with the condition of the normalization. So this is an example. You take this as a vector. Actually, this is a 2 qubits information. In terms of classical, we put them. Then this is the amplitude we calculated and constructed quantum state for each amplitude. And when you measure this, say 1 by square root 30, 2 by square root 30, 3 by square root 30, 4 by square root 30, and if you square them and sum them, total must be equals to 1. That's a normalization condition that we need to insert. And sometimes in quantum machine learning and quantum artificial intelligence system, we are very much interested for every feature that we want to take it from the system, from the nature, anywhere. But mostly in computational aspects, we take a discrete data, but we may miss out some of the very precise classical features that we use in quantum machine learning or quantum artificial intelligence, for which we need to take each classical feature. So for encoding each classical feature, we represent in terms of abstract manner x belongs to r into angular for single qubit rotation that we like in terms of polarization, ry of x equals to cos x by 2 minus sin x by 2, sin x by 2, cos x by 2, that we encode it using, by applying this on qubit 0, we can rotate this ry of x get 0, that we can put it cos x by 2 get 0 plus sin x by 2 get 1. So that we can take the data in terms of variational, so that we may not miss out any piece of information. Mostly, if you take, for example, you want to capture the pixels of our face, that we need to reach every spot in our face. For that, we need to use this kind of system so that it can capture every piece of information on our face. So if you want to capture very micro information, if you go for this approach, then we will be able to calculate every information. That's important. So likewise, that's a single qubit case. If you want to use for 2 qubits, how do you do encoding process? So we can do that by using this technique, just applying tensor products. Likewise, we can generalize this to n-dimensional systems. So finally, we need to measure, because if the data in terms of computational basis, it's already there in the certain state, we'll not be able to find, we can convert that into classical data. So if it is in superposition, mostly that we don't know exactly where the state, but we need to measure. When I measure the state, it collapses. For example, as I mentioned, that if you take a coin, during rotation, you'll not be able to measure the system. If you collapse that into, then you'll be able to find the exact output. So quantum measurement collapses a qubit from superposition to a definite state. The possibilities of outcome depends on the state's amplitudes. For example, if we take ket xi, which we can represent in terms of unknown amplitudes, alpha times ket 0 plus beta times ket 1, where it has to satisfy the normalization condition, observability value square alpha square plus beta square equals to 1. When you measure in the computational basis, which yields ket 0 with the probability, this this value square and get one with this value square. But we need to identify, choose the, we need to know, we must note the few of the important points on measurement properties. Probability. Once you measure, you will not be able to come back into superposition. That's the one of the process, always the output in terms of probability. And this measurement operator is not a unitary operator. All the gates are unitary. You will be able to do reverse process, including quantum circuitry. One of the advantages of the quantum system, you can do reverse process for entire system, but it is not possible in classical system. So that's the main feature, right? So if you take in photonic quantum computer, that the measurement system is done by devices, measurement devices. So whatever I'm talking here, mostly in terms of abstract manner, but this is the we can do simulation for everything in terms of computation, but in terms of hardware, we don't have access for hardware material. But we can understand some of the concepts how we can simulate by imagining the system. But I don't know what level you are as a learner, and we are going with the flow. So you should take this as a note, because we'll not be able to deliver everything from point to point here. So start with a qubit initialization 0. Then if you apply, it brings into superposition. When you measure, if you square it, probability we understand 0.5. If you measure this, if you square it, 0.5. We can generalize this system for any number of qubits. This is for single qubit and superposition of single qubit. We can generalize this, but we have a method for measuring for an n qubit system. That is a projective method. I go back to quantum mechanics. In quantum mechanics, measurement is modeled by a set of orthogonal projectors. We take any projector that it satisfies the outer product. This is called outer product. This notation is called Ket. This notation is called Bra. Ket-Bra notation we use for multiplying outer products. Then this we can generate this projective matrix here by using this operator, and this we can also see that the properties of that satisfies. If you transpose that projector, it remains same, and also square p square equals to pi suffix I square equals to, it remains same, and also total, if you take it, sum of all the projective matrix sum, which is equivalent to identity matrix. So you can see that those, if you are from quantum physics or quantum mechanical background, you might have understood all these, just recalling those. Okay, let the quantum system be in a state get xi equals to sigma I, where amplitude is alpha I, get pi with this condition, and outcome I is observed with the probability. This is the probability. We can see this is a bra xi pi get xi each equals to total is. The post measurement state collapses to this. Right. So as we said, I go back to once again for can you see this? As I mentioned that if we take single qubit, just I'll show you how I take it single qubit. Just single qubit I have taken. I keep the state in the 0. Then initialization, if I apply X gate, it is flipping into again 1. Again, if I apply, again it is flipping into 0 back. Yeah, this is the one of the actions of G gate, NOT gate. So suppose if I apply I gate, will not be any changes, remains same. If you apply again I gate on qubit 1 also, no change. No change you can see. So if you apply I gate on G gate, it will change the position actually. This represented minus. So likewise, you can also see that qubit 0, this one, entanglement state also we can construct. I am taking 2 qubits. Those 2 qubits get 0 here. Get 0 here. I'm putting into, this is the 2 qubits. I'm taking into entanglement state by applying control NOT gates. Now you can see get 0, 0, get 1, 1. This is the entanglement state. So if you go for entanglement state of multiple qubits, we can also put them get 0. And then I'm also constructing entanglement state, get, I'm also constructing, see, this is the entanglement state of 4 qubits. So 4 qubits, we can generalize this. This is called GHZ state, which I haven't discussed here in these slides. Next, I go with this. Yeah, so actually we do have problem today to have universal quantum computer. To build universal quantum computer, we need universal quantum processor, for which we need to use the combination of universal gates. If you use tuple gate and Hadamard gate, you'll be able to build the universal. Yeah, or if you go for C0, T, and Hadamard gate, you go for the universal. And what Goudsman Nil says, because 25 years ago we did not have quantum computer, we need to simulate the quantum circuit on a classical hardware, for which they recommended uh, simulation process, for which identified clipped groups. Clipped groups is a combination of C0 gate, S gate, and H gate. And for efficiently simulating this on classical computer, we need to use clipped gates, and also we need to follow certain criteria. That is state preparation in a computational basis, measurements in a standard basis, and classical control conditions on measurement outcomes. And so we also need to look at that computational complexity of a quantum circuit, because when you build the circuit, we need to check the efficiency of the circuit. So in the process, naturally, what you see that the two complexities which we see in computer science. One is time complexity, another one is space complexity. How much data we need to store for storage that we need to measure. And likewise, we need to see that how long it takes for doing the process, computing the process system. So these two are the criteria in computer science. One is time complexity, another one is space complexity. We measure the data in terms of bytes, bits, right? We understand that. Likewise, time also we mention. So if any finite universal gate set, if we take and a given gate set, which we measure by delta, then if L is the size of the original circuit, then that we measure in terms of number of gates, we can consider a bound L dash equals to order L log power 4 L by delta. Likewise, we also need to measure the depth of the circuit, that is the number of computational steps that we take from left to right, that we measure d prime equals to order d times log power 4 d by delta. These two are the like theoretical quantum computational problem formulas. Right. No cloning, one of the key important feature that we see in quantum, no cloning. As simple language, I explain this. When you have coin, during spinning, can you be able to measure the state of the system? No. So what I can say that the unknown quantum state you will not be able to measure. This is called the no cloning theorem. The no cloning theorem was first proposed, discovered by Park in 1970, then independently rediscovered by Vetter, Jurek, and Dirac in 1982. And it states that it is impossible to create an identical copies of an orbital in quantum states. It has many profound applications in quantum information theory, quantum cryptography and security, quantum communication, the foundations of quantum mechanics. Actually, the no cloning theorem states that there is no unitary operator U such that for any quantum state that maps U get xi in first register, second register, get E identity, which equals to get xi tensor product get xi. There is no unitary operator. Means there is no oracle, there is no oracle, or there is no gate that can copy. Right, a few of the well-known quantum algorithms. Quantum algorithms leverages quantum phenomena like quantum superposition, quantum entanglement, quantum interference. These three we use for solving many of the problems in quantum system efficiently than classical system. A few of the notable and famous quantum algorithms, Peter source algorithm, so which can break the security system. But basically, the Peter source algorithm can solve the integer factorization problem. This problem is a computational hard problem on classical computation. And in classical machine, it takes years of time, whereas in quantum machine, we can solve very efficiently. And subsequently, we can break RSA system or elliptic curve system, any other free quantum systems, but for which after Peter source algorithm is recommended, and we don't have a quantum device that can compute this process, implementation of Peter source algorithm. If we are able to implement this, we will be able to break existing security system. Mostly, we do use either Diffie-Hellman, RSA, or elliptic curve. These can be broken using Peter source algorithm. Another significant algorithm is Love-Grover's algorithm. So mostly we use for searching for unstructured data. So in quantum, structured data efficient system is better in classical system. It takes order log n, whereas quantum takes order square root n. If you want to go for unstructured data, Grover's is better. Grover's takes square root n, whereas classical takes order n. So suppose if you take for searching and Google some data, classical computer takes 100 seconds, whereas quantum takes just a 10 square root of 100 is sufficient. Another significant process is a quantum Fourier transformation. Mostly we use for a data processing, and subsequently we use this system for many of the other algorithms to implementation. So not only these, there are many promising quantum algorithms in security system optimization and simulation, artificial intelligence, machine learning, risk analysis. There are many significant algorithms that I'm not listing here. Okay, and a few of the use cases. Let us discuss cryptography. We can break classical encryption using Peter source algorithm, enabling quantum safe crypto optimizations in which we solve complex optimization problems faster than classical. In logistics, finance, and machine learning, quantum simulations, we can model molecules and identify material behaviors at quantum level, accelerating also drug discovery, material science. We can use this. And machine learning, also we can use quantum algorithms, financial modeling, in which we use for risk analysis, portfolio optimization, fraud detection, and all. So few of the use cases I put them: portfolio optimization, quantum computers efficiently explore vast investment portfolio, and we can use the algorithms like Cubo for faster solutions, which is a potential outperform against classical financial models which we see. And also we can use quantum computing for drug discovery, which can simulate molecule structures and interact at quantum level, enables accurate modelings of protein folding and drug targets, accelerates identification of promising drug candidates, reduces cost and time for traditional drug discovery systems, helps discovery novel compounds unreachable by classical simulations. We can also use for quantum security. Mostly we do know that quantum random number generators, quantum key distributions, and quantum PKs, but it's under construction. But the government of India has been focusing to implement quantum key distribution, and also we use this for quantum communication, where we can implement quantum teleportation, super densing. These things we can implement using photonic technologies. And we can also use quantum computing in supply chain, where we can have you can optimize complex logistics, routing problems in supply chain. The benefit reduces the cost and delivers timely manner with the quantum system. Next one is we can also use in weather forecasting, and we can simulate complex atmospheric and climate systems with the I values, improves accuracy of long-term weather and climate predictions, and we can also use to process large environmental data sets, and it can also support for real-time forecasting, and these are one of the identified better model. And we can also use it for stock predictions, and the quantum could perform better than the classical, and it can provide analytics for financial market and provides faster decision making for investors and traders. So thank you for listening, and if you have any questions and queries, I can reach you. Hello.
Hello, sir.
Yeah.
Thank you, sir. Thank you for giving such a lot of information. So I have one doubt, sir.
Yeah.
For easy people, if they want to do using that Quizzkit platform,
Oh.
which topic is better, sir?
I mean, what they want to do, actually, that's a key question we need to ask. Actually, what they want to implement, they want to communication system.
Communication, sir. Mostly in communication, sir.
Actually, if you look at Government of India DST portal, their target is to implement QKD protocol, and
Sir, encryption and decryption.
so may I share with your DST. This is the Government of India's portal. What they put at this, so you can look at this. Yeah, this is the information for DST funding and all. The Union Cabinet approved the National Quantum Mission on 19th April 2023 at the cost of 6,003.65 crores from 2023 to 24 to 2031, aiming to see, nurture, and scale up scientific and industrial R&D and create a vibrant, innovative ecosystem in quantum technology. This will accelerate quantum technology-led economic growth, nurture the ecosystem in the country, and make India one of the leading nations in the development of quantum technologies and applications. The key point, actually, the mission objectives include developing intermediate scale quantum computers with 50 to 1,000 physical qubits in 8 years in various platforms like superconducting photonic technology. Next one, this is the reference for electronics. Satellite-based secure quantum communication between ground state over a range of 2,000 kilometers. Within India, long distance secure quantum communications with countries, intercity quantum key distribution over 2000 kilometers, as well as multi-node quantum networks with the quantum memories are also some of the deliverables of the quantum mission. You got the point. Now another line, sensing. If you are looking for communication, this is the one. You can explore that. IIT Madras. Can you see this new screen now?
Yes, sir, it is visible, sir.
Yeah, so if you can visit this, and they are also providing funding for researchers. So what they want actually. Our mission is advanced quantum communication for secure data networks, develop indigenous quantum solutions, and positions India as a global leader, foster research, innovation, and industrial collaboration for a strong quantum ecosystem. Their focus: quantum communication, quantum cryptography, quantum innovation, real world impact, collaborations. Got it?
Yes, sir.
Yeah. Any questions, please? Technical or non-technical? Please. Hello? Yeah. I'm looking for questions. Members? Otherwise, you can ask your questions on chat box. If you speak better, if you are unable to speak, you can also write your questions. Now, I'm asking questions here, not links and all. You can ask any technical questions about this talk, not other things. You can ask other things coordinators later.
Hello.
So whatever I explained as of now, mostly that is a fundamental that if you want to understand the quantum,
Excuse me, sir.
yeah.
Sir, quantum optimization, how to do, sir? Normally, we are having deep learning optimization techniques. No?
Mhm.
So, what is the difference in the deep learning optimization and the quantum optimization?
Okay, good question. Actually. Uh, Quantum for a quantum optimization has many applications actually. Mostly, what is the main job of AI or machine learning? In machine learning, we do uh, one is such task is a common task. Another one is optimization is also a common task. These are actually fundamental functionalities of a quantum machine learning and quantum AI. So, of course, for quantum machine learning and AI, we do have QA, quantum optimization and quantum approximate optimization algorithm, and QAV, quantum variational encoder. These algorithms already there, which we can use for hybrid system, classical to quantum, quantum to classical, and you can use. But the area which you need to work mostly, if you are interested to work on machine learning and AI, not only those two, because whatever the functionalities we have been carrying on a classical system, we can be able to carry same functionalities on a quantum system, which are lack. We don't have many of algorithms. That's why if you are able to build any of the quantum machine learning, quantum AI algorithms, you will have a lot of scope to do research. Focus on those areas so that you will have more scope. What kind of function task you are doing right now? Uh, Same thing you can enhance using quantum model and compare that which method is better, classical or quantum, and you can do that where your research. Suppose you are doing something in quantum machine learning or quantum classical optimizations, not quantum, and the same functionalities you can work out, but algorithm will not work same manner because the processor for quantum is totally different than classical. You can't implement, if you implement a classical algorithm on quantum, you will not be able to see the advantage. You need to take advantage, quantum advantage, and for which you need to use quantum processing method, and you need to build quantum algorithm such a way that where you are using quantum features like a superposition, entanglement, and also interference are also no cloning property. If you build use algorithm using these features, you can see the better performance, and you can prove that quantum optimization is providing better optimization than classical, and provide the your algorithm or solution. Yeah, please ask a question.
Thank you, sir. Thank you, sir.
Yeah,
Excuse me, sir.
yeah,
Am I audible to you? This is Varshita here.
yeah. Yes, please.
Sir, actually, I'm pursuing my PhD with photonics. I mean, broad area is photonics. The
Okay.
name I have given is Design Analysis and Optimization of Integrated Photonic Based Devices for Communication Applications. So, if you could just give me a hint, like what exactly is going on with sort of the communication applications with respect to the quantum, I mean, quantum related to the photonics, just a pathway. So where I can inline my PhD uh, uh, thesis or the work that I've entitled for.
Okay. Sorry, from which university?
Sir, it is Vishveshwaraya Technological University, Belgavi.
Belgavi. Okay.
Yes.
Uh,
I am. Uh,
okay.
Yeah, I just wanted the pathway because I have pursued my MTech in nanotechnology basically.
Hmm.
So I have taken this into consideration because I have the background of EC in my BTech also. So just give me a hint, like what exactly is going on with respect to the communication applications in line with the quantum and the photonics.
Yeah, okay.
So I can.
First of all, thank you. And you can also contact me after this session, because
Okay.
we are also focusing on photonic-based quantum communication and computing.
Okay.
We are also establishing a lab for photonic quantum technologies in Hyderabad.
Okay, sir.
And we are also picking the team from across the globe who are experts in this domain
Okay.
to work out for our R&D activities.
Okay,
So
sir.
our main focus, because if you take superconducting, I want to give some idea that why we don't choose superconducting for communication.
Okay.
To do computation in
Ah.
using superconducting, very good one. I say even very good even for communication as well. Why? But I don't recommend to use it. The reason I tell you. Superconducting material is a scalable material for computation. If it is a good material for computation, why can't it be good material for communication?
Yeah. Okay.
That's a question we should raise. But in superconducting material, we use zero resistor. That's not semiconductor. We use zero resistor. For maintaining zero resistor and processor, and we only challenge we use there 0 Kelvin temperature. So under 0 Kelvin circumstance, it can work well without any noise and disturbance. Under 0 Kelvin means minus 273.15 degrees Celsius.
That is a little bit tougher to maintain throughout. Yes.
Yeah, in
Yes.
environmental communication, it is open system.
Yes, sir.
So that is tough part. That's why we eliminated superconducting material for a quantum computation.
Okay. Okay, sir. Okay.
Second material is photonic material.
Okay.
Only advantage of the photonic material, it can work at a room temperature. Room temperature is a normal environmental temperature, right?
Yes, sir.
So that is the best fit hardware for quantum communication.
Okay.
But it is under experimental stage. Already China has implemented up to, I think, 2,500 kilometers. They implemented quantum teleportation.
Okay. 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 Okay.
Our government of India is also working on that with the CDAC and CDAC, I think DRDO and other IITs together. They also recently put it something in media that they put it up to 1 kilometer.
Okay, sir.
So if you apply for funding and work with some of this, you'll be able to get so a lot of things to whatever communication, like a wireless communication, quantum wireless communication, we don't have.
Okay.
So these quantum satellite-based system, mostly the promising things that the government of India, quantum fiber optical networks we have, right? Optical.
Yes, sir. Yes, sir.
So,
OFCs we do.
yeah, if you focus that, it's mostly based on photonic, light-based.
Okay, sir.
If you focus those areas, you will be able to get the stuff that you want. I
Okay,
don't
sir.
know exactly what is your problem statement for your PhD, but you can
So
have.
basically, we are trying to have the quality factor improvement with respect to the WDM and DWDM, all these aspects, sir. So we have just taken it in a broad way, and there is one other person who is going to work on the photonics with respect to the sensors, like biosensors, all these different kind of sensors. Her intent is with sensors, and I am having the communication application. So I just wanted to hint, you get the hint, like what exactly, how I can inline through this. So,
I think mostly challenging for you to get material and experimental work.
yes. So
Only you can do simulation as a student. As
yes,
a student, you can do that mostly simulation.
yes, sir. We are just working with the console software, sir. But
Sir,
Yeah,
sorry for the interruption.
yes, sir. Yes, ma'am.
Day after tomorrow, we have another session, sir. He's from Srinivas Talabatala from IISc Bangalore, sir. So
okay.
completely that the topic is on photonics.
Okay.
Okay,
Um,
Okay.
okay, okay,
Sir,
ma'am. I just noted
followed
down.
by a sir session also, madam.
Okay, okay,
He will
ma'am. I have
continue.
noted it down. I'll join the same. Thank you, ma'am.
Okay.
Sir, on that day also you have another session, sir.
Photonic,
Day after two. Yes, sir. Continuation session.
okay, I'll join for photonic now.
Okay, sir.
So I don't know, madam, you can contact me and
Okay, sir.
can provide
I
more.
shall collect your details from madam, and I shall make the call.
Sure, madam.
Thank you so much.
I will share sir details in WhatsApp group, madam.
Thank you so much, ma'am. Thank you so much. Thank you, sir, for
Yeah. So
talking to me. Yes, thank you.
mostly questions from outside. Any of these questions from this talk?
Yes, sir. Thank
I'm
you.
happy to ask questions from this talk.
Okay, sir. Thank you so much.
Because the madam requested to provide mostly the basics. I went for basics today's session. And we know that in 1 hour time, we'll not be able to deliver everything. But if you're able to catch up some of the ideas, and they can you can explore later. That's the idea that we deliver this panel. Yeah. Yeah. Any other questions? Hello.
Roja madam. Roja madam.
Maybe she is not there. Conclude it, Hema.
Thank you so much, sir, for your valuable talk, and your insights have been very much helpful to the research scholars, those who are entering into their research related to quantum technologies. And uh, uh, participants, if you have any other questions, please raise. Otherwise, we can conclude the session. Vishnupriya ma'am, can I conclude the session?
Okay, ma'am. Okay. Sir, participants, if there is any information you needed regarding this, I will share it in WhatsApp. So you follow that one. Thank you, one and all, for actively participating in this FTP. Thank you, sir. Thank you very much for
Yeah.
sharing a good hello.
Yeah, madam.
Ah, thank you, sir. Thank you very much for sharing such a good topic in this. And we need more practicality also, sir.
Yeah, I can because I can provide Peter's, I mean Grover's algorithm, and I will
Okay, sir.
also
How
provide.
to execute one particular algorithm in one particular tool.
Yeah, sure,
Ah,
sure.
okay, sir. Thank you, sir.
Okay. I'll also correct that. I already corrected the.
Okay, okay.
Sorry for that error. Yeah, right, madam.
Okay, sir. Thank you, sir.
Right.
Thank you so much to one and all. Tomorrow we'll have a session, 2 sessions. Again, links will be shared tomorrow. The same link will be shared in the WhatsApp group tomorrow as a reminder. And please join before 10 minutes for a smooth connection.
So tomorrow is completely on artificial intelligence.
Okay.
Yeah.